So I hope my slide is visible. That is with example. Yes.
Yes, ma'am.
And it is in PPT mode.
Yes.
Okay. Thank you. So good morning to you all. In today's class, we will discuss again the shell and tube heat exchanger design. And if you consider the previous class, there we have focused on Bell's method. And this Bell's method is specifically for shell side design of shell and tube heat exchanger. Tube side design will remain same as we have discussed in previous approach, which is like Kern's method. I should not say Kern's method because that is general method. Kern's method, Bell's method, all these are for shell side only. Okay, so Bell's method, when we have seen, let me revise that quickly and then we will start this class. So Bell's method, when I'm saying, it is for shell side heat transfer coefficient as well as shell side pressure drop. Okay, so when we see the heat transfer coefficient, we have considered the ideal condition first, and then we have considered different correction factors related to other conditions like cross flow, window correction, and we were having bypass as well as leakage. All these we have counted with a respective correction factor. Okay, so that is for the heat transfer coefficient. For pressure drop, we have focused on different zones. Just 1 minute, please, sir.
Yes, ma'am. ये प्रोग्रेस रिपोर्ट है। ये मैम ये एक्सटेंशन वाला है मैम, 5 से 5.5 साल।
कितना साल हुआ आपको?
5 हो गया मैम। थोड़ा सा एक्सपेरिमेंट हो गया।
Thank you, all the best. As far as pressure drop is concerned for shell side, that we have discussed with the different zones. Okay, we have cross flow zone, we have window zone, and we have end zone, and we have seen how to find out the pressure drop in each zone, and depending upon the number of these zones, we have calculated the overall pressure drop in the shell side from inlet to outlet. Okay, so in that way we have focused on shell side design using Bell's method, and this is the related example. If you see, the example is like here I am having 20,000 kg per hour of kerosene, leaves the base of kerosene side stripping column at 200 degrees Celsius and is to be cooled to 90 degree by exchanger with 60 to 2500 light crude oil available at 50 degrees Celsius. So you see the fluids which we need to which little bit like with more information, as we are only focusing on shell side. Okay, so tube side information, whatever is required, that is already available to us. Okay, so therefore the information is more. Otherwise, if 5 parameters will be given to you, tube side calculation you carry out following the previous example, uh, and then you can proceed for shell side calculation. Okay, just 1 minute, please. Okay, so if you see further, pressure drop of 1 bar is acceptable for both streams, means for shell side as well as tube side, so that we need to consider while designing. Allowance should be made for fouling by including the fouling factor 4 into 10 power minus 4 on crude stream and 2 into 10 power minus 4 for kerosene. Okay, and uh, further carbon steel material is given for shell side and tube, and we need to consider split ring floating head specifically for this heat exchanger, and design we used to do with Bell's method. Okay, if you consider other information which are available, 19.05 OD of the tube and 14.28 ID of the tube, 5-meter long tubes are used with the triangular pitch. So all these information are available in this particular problem. Otherwise, that you can also figure out, okay, based on the last example which we have considered in Kern's method. Okay, assume HI as 920. So if you see, tube side calculations are already done, and information that it is already available. So don't need to proceed for tube side. We will directly proceed for shell side. Number of tubes which are given as 300, and the spacing, baffle spacing is ds by 5. Okay, so we need to calculate ds. Number of tubes are given, and we will consider 1 to pass, okay, as initial guess. Okay, now if you consider the properties which are given over here at so don't need to collect the properties, otherwise procedure you are already aware of. Okay, so that you can follow, but here it is, these properties are already given. So if you see, first, whatever calculation we proceed for shell side, using Bell's method, you need to find out HOC. Okay, HOC will be based on Reynolds number, and Reynolds number will based on that shell side velocity, which we call as US. Okay, cross flow shell side velocity. Okay, and for that you need to find out AS and all, which is similar to Kern's method. Okay, so that you need to consider, but for that velocity and all, we need to decide the flow rate, which flow rate we should consider, and for that we need to allocate the fluids to shell side or tube side. So if you consider here, the fouling factor is like more fouling factor you are given with crude stream. Okay, crude oil has more fouling factor in comparison to kerosene, and we know that fluid having lesser fouling tendency should be allocated to shell side. Okay, so in that case, kerosene should be allocated to shell side. I hope you are getting my point, and for that flow rate is given as 20,000 kg per hour. Okay, so as I have told you that we need to proceed for HOC calculation. Uh, just a moment, sorry. So HOC calculation we need to proceed. For that, as I have told you, we need to find AS and US. So for AS we need shell dia, that is DS. Okay, for DS we have we should consider first bundle dia, and bundle dia expression you know already. Number of tubes we are given as 300. So K1 and N1 we can consider for triangular pitch with 2 passes. Okay, 1-2 pass, right? So we have to calculate bundle dia, which is coming as 474.1 mm. Okay, this value I can take, right, for K1 and N1 that you can see. Okay, we are given we need to find out the shell dia. So for that we need to find out the clearance, and clearance bundle dia you have already calculated 4 points 0.47 somewhere, something like that, and split ring floating head heat exchangers, that is given to us, and corresponding to that, the clearance we can find as 58 mm, and shell dia you can calculate further. And once I'm having the shell dia, we need to find out AS, where baffle spacing is required, LB. Okay, so that is DS by 5, so 106.4 that you can calculate. Okay, DS by 5, that is already given. Okay, so nothing to assume about that, you can take that, you can consider that directly. So AS, that is cross flow area we need to find out, so that we can calculate like this. And once I'm having this AS, we can find out shell side, cross flow velocity, and that is with 20,000 kg per hour, which is nothing but the flow of kerosene which we have allocated to shell side. Okay, Reynolds number you can find out once you have with this US, and that Reynolds number it will consider DO instead of DE. Okay, because we are considering that it is the ideal tube. Okay, and ideal tube bank, it means one tube flow will not hinder other tubes flow, so therefore instead of DE we are considering OD of the tube, right? So that is Reynolds number for shell side, value is this 2.17 times 4. Prandtl number we need to find out, and then we can find out Prandtl number. For that, properties are already given. This is K, Cp mu by K, not R. Okay, so this is K. Okay, so Prandtl number you can calculate, and to find out heat transfer coefficient HOC, we have to see the value of JH, and that you can see from this graph. Okay, this is in volume 6, so you can see this is the, if you see 2.17, so 2.17 it is around here into 10 power 4, and the value is slightly lesser than this 6, so we can consider 5 point like 5.9 or so into 10 power minus 3. Okay, you need to see the value of all these factors as uh, clearly as you can. Okay, so HOC you can calculate, you can find as 1780.94 watt per meter square degree Celsius, and once you complete that, we will proceed for correction factors. Okay, actually this is my suggestion to you all, as uh, you are already having volume 6, I guess. Okay, if you don't have, please let me know, and whatever topics I am covering, related examples you can solve from that. Okay, and other problems I will also give to you, but that problem you will not find in book, so it is better to practice, or to design, or we can say to uh, uh, carry out the calculation. You can do the examples on your own, okay, for your understanding, right? Just 1 minute, please. I'm so sorry. So that is actually that I was saying that you need to solve the example of from the book. Okay, so once you have this HOC value, you can find out the you can go for correction factor calculation. So first of all, we need to find out this Fn, that is uh, cross related to cross flow, and for that we need to find out the we need to observe first the Reynolds number. So if you see, Reynolds number is this, which is more than 2000. So we will proceed for the graph. If you remember, uh, this is the graph, and here we need to see we need to find the value of NCV, and then we can see Fn value. Okay, and this NCV, if you see, this is the expression which we have discussed in the last class, dB minus 2 HB by PT prime, and this HB you can find out by this expression. So HB you can calculate. Okay, BC is to 0.25. It is not given in the problem, and but it is like 25% baffle cut is the optimum value which you should start with. Okay, so in that way you can consider BC as 0.25, and DS and all DB, that values are already available with you, so you can find out HB. Once you have HB, you can find out NCV, and which is all parameters are given. And I would like to mention that this PT prime you need to consider, and here pitch is given as triangular pitch. Okay, so PT prime would be 0.87 into PT. Okay, and PT is what? 1.25 D naught. Fine, that all we have discussed before. So 1.25 D naught, it is that it is PT, and 0.87 because of the triangular pitch. And once you do that, you need to consider NCV as 12.839. Okay, and as we have discussed that NCV is the complete number, right? NCV is the complete number, and that cannot be in decimal, so you need to consider the round up value. So here 12.8 is there, so you need to consider 13. If it is 12.2, then also you need to consider 13. Okay, so here NCV you need to round up, right? What you need to do further, that we will discuss, but NCV should be round up. Please make a note somewhere. Okay, and once you have this NCV 13, you can find out Fn from this graph, which is coming as 1.01. So it is not very much complicated. Only NCV you need to round up. Okay, so Fn you have calculated. Now we will proceed for window correction factor, that is FW. For FW, you need to find out RW, which is 2 into RA prime. That all we have discussed in the last class. And RA prime, if you see, RA prime is this is not RA1, this is RA prime, and this is the graph for this RA prime. And RA prime we need to see from bundle cut. Okay, this is the only graph which is available, the above one, and you need to calculate, you need to consider RA prime at bundle cut, not at baffle cut. Okay, so bundle cut when you are considering, that is nothing but HB by DB. Okay, and HB, DB, all these value you know already, so it is coming as 0.22. However, if you consider baffle cut, on which this RA depends, which we will use further, so that baffle cut is 0.25, 25%, right? So baffle cut is 0.25, bundle cut is coming as 0.22. Okay, so once I'm having this bundle cut, we can see RA prime from this graph. Okay, and that you can see very well. So once I am having this RA prime, we can calculate we can calculate RW, just twice of that. And once I am having this RW, we can find out or we can see FW using this graph, using this graph where RW 0.32 is given. Okay, so somewhere you can find the value. So it is coming as 1.06. Okay, so depending upon this RW, FW you can find. And once you see the calculations, the computation or finding the values of correction factors, that is not very difficult. Only you need to understand what parameter you need to choose to find the values. Okay, now once I'm having this FW, we can proceed for FB calculation, that is bypass correction factor. Okay, and once I'm having this bypass correction factor, it basically counts stream C. Remember, in the last class we have discussed. Okay, so stream C, that lies in the clearance between shell and bundle. Okay, and the effect of this bypass stream, that can be what we can say, somehow compensated by providing sealing strips. Okay, so FB, when we are considering, this is the whole expression. Okay, but first of all you need to find out whether sealing strips are required or not. Okay, so we will consider this, whether sealing strips are required or not, and if sealing strips are required, then how many sealing strips should be used. Okay, that we can see. Okay, so this is the expression. So to know that whether sealing strips are required or not, we will consider NS0 over here. Okay, first of all we are considering that no sealing strips are used. Okay, so NS should be 0 over here. Then we can proceed for FB calculation. Okay, if FB value you are finding more than 0.6, okay, FB value you are finding more than 0.6, it means no sealing strips are required. Your design will be feasible without sealing strips. Okay, I hope you are getting my point. FB should be greater than 0.6 if NS is 0. Okay, if it is coming less than 0.6, it means that FB value is low enough and it will bring your design to infeasible condition. Therefore, you need to provide sealing strip to increase the value of FB. Okay, so if FB value is less than 0.6, it means sealing strips are required. Okay, and if sealing strips are not required, you need to use this graph. Okay, or whatever value you can obtain by putting NS equal to 0, that will also be same as you can see from this graph, but a little bit variation may be there, so you can see this graph. Okay, it is better, but the value will not differ much. Just a moment, please. Okay, so you can see the how we will choose whether sealing strips are required or not. And in this problem, if alpha you need to consider, depending upon the Reynolds number, you can choose the correct value of alpha. Okay, and for this N is equal to 0 in the present problem, NCV, if you consider NCV, we have taken as 13, right? And AB and AS, all these we can calculate. There is no difficulty. So once I do this, FB value at NS equal to 0 is coming as 0.479, which is less than 0.6. It means that sealing strips are required. Okay. And if sealing strips are required, next calculation will be how many sealing strips should be used. Okay. So maximum value of sealing strip should not be more than NCV by 2. Okay, NCV I am having 13, but 6.5 number of sealing strip you cannot use. You can use maximum up to 6. Okay, because that is the strip. It won't be in decimal. Okay, so maximum NS value should be 6. Right? So what you have to do now to NS is the NS equal to 6 is the maximum number. Okay, but how many sealing strip will work for you? Okay, that you need to decide by putting this NS by NCV with variations like 1 by 13, 2 by 13, like that up to 6 by 13, because NS more than 6 you cannot use. NCV is 13 always. So AB by AB and AS, that is given alpha, you can choose, and you have this expression. Once you put these NS by NCV different value, you can find out FB value like this. Okay, so which how many number of sealing strips would be required, it will depend on this FB value. Okay, so FB value, by putting the correct number of sealing strips, should be more than 0.85. Okay, so when at whatever number it will get the value 0.85, even if you can see this is 0.84, but it will not work. Okay, 0.85 and more than that, whatever uh, FB value you obtain at whatever NS number or whatever sealing strip number, that you need to consider. So in this problem, correct number of sealing strips are 4. Okay, and FB value or bypass correction factor you can obtain as 0.896. Okay, in this way you need to choose the bypass correction factor. Okay, so once you need to choose whether sealing strips are required or not, and then you can proceed for necessary number of sealing strips. Okay, so I hope approach is clear to you. And once I'm having this FB, we need to find out FL, that is leakage correction factor. And this leakage correction factor we need to consider okay. If you see, this is the expression for leakage correction factor. We need to find out beta L, and it will depend on this ATB plus ASB, and AL. AL is ATB plus ASB. Okay. So so first of all, we need to find this ATB and ASB. ATB, if you see, this is the expression, and W, that is number of tubes in window zone. Okay, and that we can find by this expression, NT into RA prime. ATB you can calculate. CT will always be 0.8. Remember, we have discussed yesterday, 0.8 mm. Pi d naught, that we can see by 2 NT minus NW. So you can find out ATB as 6.03 into 10⁻³ meter square. Okay, and we can find out ASB using this expression, CS ds by 2 pi minus theta b. Okay, so here you need to find out CS and theta b. Okay, CS would be will depend on the shell dia. Okay, if you see shell dia here is 532, and this is the table we have discussed yesterday to see the value of CS. So if you see, 532 will lie over here. Okay, and it will lie here as well. Okay, so if it is pipe, it is falling in pipe shell as well as plate shell both, we need to choose for pipe shell. Okay, so in that case CS value should be 1.6 as you can see over here, right? And theta B you can find out from this graph using this below curve, and theta B should be this is the angle made by chord of baffle. Okay, so it will be seen at baffle cut, not bundle cut. Please keep that in mind. So 0.25 whatever value is coming, 25% baffle cut we have taken, right? So based on that, whatever value is coming, that you can see as theta B, which is 2.1. Putting all these values in this, you can find out ASB, which is 1.78 into 10 power minus 3. Addition of these two will give AL. Okay, so once I'm having this AL, we can find out, we need to find out this beta L from this graph. Okay, AL by AS we need to consider AL by AS. Okay, AS from where? AS we have already calculated before for HOC, remember? So that we can consider here directly, and AL by AS you can see is 0.69. So 0.69 around 0.7, and in that case you can see the value of beta L as 0.41. Okay, for that FL you can find out as 0.496 around 0.5, right? So once you have this, you can have you can calculate HS, shell side heat transfer coefficient. This is HOC, and these are all correction factor. Okay, FB value you need to consider which is more than 0.89. Okay, so that you can consider with this FB value, and HS you can consider as 848.21 watt per meter square degree Celsius. So in this way you can find out shell side heat transfer coefficient using Bell's method, right? And now we need to proceed for pressure drop. Okay, so as we have discussed yesterday that pressure drop will be should be calculated for different zones. So first of all I'm having this cross flow zone, that is delta PC, which is equal to delta PI FB prime, or FB prime into FL prime. So delta PC, when we consider, first of all we need to find out delta PI. Okay, and then these correction factor delta PI, this is the expression. NCV we know already, 13. US we have already calculated before. Okay, Reynolds number, this Reynolds number for this JF you know already, because Reynolds number you have calculated previously, and JH here it should be JF. Okay, not JH. Okay, so considering the JF value, okay, from the graph you can find out delta PI as 1026.014 Pascal, that you can calculate. And once I'm having this delta PI, you can find out FB prime and FL prime. FB prime, for that number of sealing strips you have already fixed to 4. Okay, number of sealing strip NS should be 4. Alpha value you can choose as 4. Okay, depending upon the Reynolds number, and you can find out FB prime 0.722. Okay, so here you don't need to consider whether sealing strips are required or not, how many sealing strips and all that. All we have fixed in heat transfer coefficient. You need to use all those values directly over here. Okay, so this is FB prime. Okay, similarly you can find out FL prime. All these ATB, ASB or AL, all these values are known to you. Only you need to find out beta L prime from the graph, which is given over here, AL and ASB 0.7 around. So that you can see. So value of this beta L prime would be equal to 0.65 and FL prime you can see as 0.28. Okay, now once I'm having this FL prime, we can find out delta PC by multiplying all these correction factor with delta PI. No complicated calculation is there, it's simple, so you can do. So delta PC you can obtain as 149.5 Pascal, okay, like that. So pressure drop, when we are considering the for window zone, this is the expression. Okay, and cross flow zone we have already done delta PC. Window zone pressure drop delta PW, this is the expression FL prime 2 plus 0.6 NW rho UZ square by 2. And this UZ, if you see, this is the geometric mean of UW into US, and UW would be the velocity in window zone. Okay, and it will depend on this AW. Okay, actually all these expression we have discussed in the last class, nothing new. Okay, only you need to see the expression. So AW you need to find first. This is the expression for AW where RA would be used, and RA you can see at baffle cut, not the bundle cut, remember. So that RA you can find from the graph as 0.17, at baffle cut 0.25. Okay, NW we have we already. Okay, yes. Sorry. This graph you can use 0.25 pe RA you can see. Okay, so in that way RA you can find out 0.17, NW you can calculate, and AW you can find as 0.0241 meter square, and so UW you can find 0.316 meter per second. Okay, and so you can find out UZ. US you have already calculated before, so UZ you can get as 0.46 meter per second, and density that is given as a property NWV. NWV is the number of vertical tube rows in window zone. Okay, so that you can find as HB by PT prime, because we are considering triangular pitch. HB you know already, PT prime 0.87 into PT, that you can calculate. So it is coming as 5.0224. Okay, now here you should consider this NWV should be round off. Okay, if you consider this NWV and in cross flow number of vertical tube rows NCV you have obtained. Okay, so you can consider NCV as round up and NWV as round off. Okay, if you do round up for both or round off for both, the number of tube rows will differ. Okay, so NCV should be round off, or NCV should be round up and NWV should be round off, or vice versa. You can make this round up or NCV round off, no problem. Okay, but you need to consider uh, up for one and off for another. Okay, so you can consider NWV as 0.5, and FL prime you can find sorry uh, okay, so NWV you can find as 5. FL prime we have already calculated before, so delta PW you can calculate using this expression, which is coming as 78.17 Pascal. Just a moment. Um, so in this way you can find out the pressure drop for window zone, and uh, lastly we need to find out the pressure drop in end zone. Okay, so this is the expression for pressure drop in end zone, and delta pi we have already calculated, and this is the total number of restrictions which needs to be crossed by liquid, okay, at end zone. Okay, so NWV plus NCV by NCV into FB prime. So all values you know already. Okay, so you can find out delta PE as 1025.7 Pascal, and once you do this, you have calculated pressure drop of each zone. Now we need to count the number of zones, and just 1 minute, I'm so sorry. Hello. हाँ 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 अच्छा ठीक. So once we do this, uh, we need to count the number of zones, and number of zones like two zones of end, and we have NB minus 1 cross flow zone and NB window zone. Okay, so we need to find out NB, that is number of baffles, how we need to uh, count, and that number of baffles should be capital L by LB minus 1. Okay, so that you need to consider. L is the length of the exchanger, which you can consider as length of the tube. Okay, so because length of the tube will decide the length of the exchanger. Okay, length of the shell also. Okay, so capital L by LB, that is number of tubes by LB minus 1. Okay, so number of sorry capital L by LB minus 1. Capital L is 5, which is the length of the tube. LB you can see like this, you have already calculated minus 1, and that is coming as 45.98. I am considering 45, though it is close to 46. You can consider 46 because it is very less difference is very less. However, in general, we consider this practice that NB should be round off, okay, not round up. Okay, and the reason is because length is fixed. Okay, so number of baffles you can consider as that which is like, because length is fixed, so you cannot accommodate the extra one. Okay, so that number of baffle should be 45 in this case. Okay, this 5 is in meter and this is in mm, don't get confused with that. So here it should be 5000. I hope you are getting it. Okay, so once we do this, we can find out NB, and then you can use this expression. So this is coming as 0.1214 bar, which should be less than 1 bar. So in that case, our design is feasible. So in this way, you can use Bell's method to find out the heat transfer coefficient and pressure drop in shell side, and so you can use this method for design of shell and tube heat exchanger. Okay, and that is all about the design of shell and tube heat exchanger. We have discussed two different methods, Kern's method and Bell's method. And if you remember, Bell's method limitation is it does not count stream F, okay, which is the that pass partition plate stream. Okay, if we count that, we have another method that we call as stream analysis method. Okay, and that stream analysis method, it is given in RW Surth book, not in volume 6. So if any one of you is interested to read that, you can refer that book. If that book is not available to you, please let me know. Okay, RW Surth book, in that the stream analysis method is given after this Bell's method, so that you can see. Okay, so in that way we complete the design of shell and tube heat exchanger, and now I will show some of the images like heat exchangers which are very large in size. As you can see, the tube plate, that is this tube sheet, that is very large. So this type of heat exchangers you can consider. And if you see, this is nothing but the baffle. Okay, these are the baffles. Okay, these are the actual baffles. Okay, and number of tubes you can insert in between these holes. So you can see the pattern over here. This is the triangular pitch, right? This is the triangular pitch pattern. Okay, so in that way you can visualize the heat exchanger, which are quite large in size. And if you are able to see these rods, okay, one rod is here, another rod is here, this is another rod, these are tie rods. Okay, these are tie rods in which you insert the baffle spacing. Okay, and if you observe the scale formation, this is like this. It looks very dirty, and that scale deposition means the fouling condition. This is when material is deposited, so it looks like this. So we need to we need to carry out regular maintenance to remove all this, and for that some chemical and mechanical treatments are done in tubes. So if you observe this, if this type of material will be accumulated in the shell, this is over the tubes. Okay, you see here we have the tubes, and inside this also, if some corrosion or scale formation is there, it is easy to clean that because tubes are straight. However, if this type of deposition will occur in the shell in between tubes, okay, it is very difficult to clean. Therefore we consider, like while allocating the fluid, we consider one principle, that whatever bad we used to do, that we should do with the tubes, not with the shell. Okay, so this is the scale deposition, and in this way we can have the corrosion which in which material loss is there because of the reactions. Okay, but in scale formation material is deposited. Okay, so in this way you can consider corrosion, and these are some of the images which I have shown you. So that is about the shell and tube heat exchanger design, and I'm giving you these two problems. Okay, the problem one is using Kern's method, in which 50,000 kg per hour of liquid ethanol at 90 degrees to be cooled to 45 using shell and tube heat exchanger with this much flow of water which is available at 15 degree. Pressure drop of 1 bar is permissible on both the sides, shell side as well as tube side. Okay, so this you need to design using Kern's method, and this second problem you need to do using Bell's method. Okay, so all dimensions are given over here. These are the fluid parameters, and these are some geometrical parameters. So you need to solve these two problems on your own. Okay, and because the solution, when you are considering solution, even Kurt's method or the complete heat exchanger design, if you are considering, it will take at least 2 hours or more than that. Okay, so I will give you sufficient time to solve these two problems, and these solution of these two problems I will discuss on Sunday. Okay, that will be on 25th. Okay, so 25th class we will discuss the solution of these two, but that only I will discuss if you solve on your own. Okay, so I will ask the values of parameters from you only. Okay, and then I will clarify whether it is right or wrong, and if it is wrong, why it is wrong. Okay, and like that only. Okay, so volume 6 you are already having property tables I have already given. Okay, in through this what we can say, in the video we have discussed that property, and if you require that PPT separately, that I will let you, I will give it to you, but please drop an email for that. Okay, otherwise that is available in the video, or that is available at back of Sir's book also, if you can see from there. Okay, so solve these two problem, and then solution of that we will discuss on Sunday. Okay, and that is about Schelling tube heat exchanger. Just after 2 minutes I will start another topic. Okay, so please give me 2 minutes time. So I hope my screen with the design of condensers, it is visible. I hope it is yes. Okay. So when we consider the Schelling tube heat exchanger, that we consider as the streams in which you need to heat up or you need to cool down the stream, and that is related to when in both the streams we need to have the sensible heat transfer. It means in both the streams we should have temperature variation. Okay. So sensible heat transfer, when we consider, that is always the case that we sense some of the variation in temperature in both the fluids. Okay, that is the meaning of sensible heat transfer. Otherwise that would be phase change. Okay, so in shell and tube heat exchanger, whatever we have discussed so far, that is for sensible heat transfer. And you must have observed that we observe temperature variation in both the fluids. Okay, either it is shell side or tube side, doesn't matter. However, another type of exchanger we have is the condensers, which are um, which are used in what we can say, used in chemical industry very widely. And these condensers, when we consider, um, you all should aware that these are used to convert the what we can say, the uh, phase from gas to liquid. Okay, so used in chemical industries, and these are used to condense the vapor, condense the steam, or not, that condensation is done by providing the coolant. Okay, so most condensers used in chemical process industries are shell and tube heat exchanger or air cooled heat exchangers. Okay, air cooled heat exchanger, that also we have discussed while discussing classification. Okay, and when we consider air cooled heat exchanger, in which air is used as a coolant, and in a shell and tube heat exchanger, usually coolant is the that water. Okay, and the in air cooled heat exchanger, condensing vapor flows inside the bank of in tubes, and ambient air blown across the tubes by fan, which serves as a coolant. So air will be used as a coolant in air cooled, otherwise mostly coolant is water. Okay, so the purpose of condenser is to provide the liquid stream out of vapor or out of steam. Okay, uh, and you are aware of that as far as chemical process industries are concerned, where these condensers are used. Mm, so we will discuss some of the application of this condenser, though I believe that you people are already aware of that. So we will see the usage of condenser. The first use, we can say, the very common, everybody knows, being a chemical engineer, that it is used in distillation. Okay, other usages are in refrigeration and in power cycle. Okay, so these are used widely in chemical and petrochemical industries. Wherever I am having these units like distillation, refrigeration, and power generation. Okay, and when we consider these application one by one, let's say if I focus on distillation. Okay, distillation, if we consider the top of the distillation column, we have one heat exchanger, which is this condenser. Okay, so condenser is used to convert the vapor which is exiting from the top, to convert that vapor into liquid, because in distillation column we need vapor and liquid interaction. Okay, so vapor and liquid stream should be available in the distillation column, but when we consider vapor at the top, okay, uh, it enters the condenser, and uh, during condensation liquid forms, and then that liquid returns back to the distillation column, and that we call as the reflux. Okay, and when we consider L, which is the stream which is coming back to the distillation column, by R, L by R, L by D if I consider, D is the distillate and L is the liquid which is coming back to the distillation column after condenser. So L by D is basically called as the reflux ratio. Okay, so that you already know, and that reflux ratio you cannot obtain until unless you will not pass the vapor through condenser. So the importance of condenser that you can see, and once I'm having that reflux uh, through condenser, uh, we can see the purpose of condenser. Okay, we can see the purpose of condenser as when purpose of condenser that you know, right, it is used to convert vapor into liquid. Okay, but my point is different over here. Like when we consider the distillation column, okay, we consider two type of condenser. Okay, one is partial condenser and another is total condenser. Okay, partial condenser and total condenser. Okay, partial condenser, you understand, that is what we can say, some amount of liquid. Okay, some amount of liquid, it is returning uh, sorry, partial condenser, when I am telling, it means some amount of vapor will condense only. Okay, some amount of vapor will condense only. And if you see the working of distillation column, reflux is must. Okay, that L stream is must. Okay, so on which it will depend on which factor that I should need partial condenser or I should need total condenser. Okay, because liquid is must. Okay, it will depend on the product nature. If product of the distillation column, that is distillate, okay, if that distillate will be required in vapor form, right, if that distillate is required in vapor form, we consider partial condenser. And if that distillate is required in liquid form, we consider total condenser. I hope you are getting this. Okay, so with distillation column we have partial as well as total, both condensers, in which case which one should be used, that I have already told you. Okay, so that is about the distillation column. Another usage of that condenser is in refrigeration, in which I hope you remember the refrigeration cycle that you must have read in thermodynamics. Okay, it has evaporator, it has compressor, it has condenser, and then it has throttle valve or expansion valve, right? So this cycle you know already. So when the purpose of refrigeration is it takes heat at lower temperature and rejects at higher temperature. Okay, so higher temperature heat rejection will be done in condenser. Okay, so condenser is a part of this refrigeration cycle, and it is used to liquefy the high pressure refrigerant vapor leaving the compressor. Okay, so that you can see. Okay, so in this way you can consider the use of this condenser in refrigeration. Next is use of condenser in power generation, or you must have aware of that Rankine cycle. Okay, Rankine cycle, what will happen, that we are having that boiling, and then uh, what are the different components of that, like we have preheating of the water, then boiling to get the steam, and then turbine, and then condenser, and after that it comes through pump. Okay, so before pump, condensers are used. Okay, because when the steam is thrown over the turbines, okay, it runs the turbines, and so the power generation occurs, but during that turbine movement, the part of the vapor, part of the steam gets condensed. Okay, so that is automatic. Okay, for that condenser is not required because expansion is there while running the turbine, so steam part of the steam gets condensed automatically. Okay, so why we need condenser? Okay, the purpose of condenser is whatever unconverted part of the steam is there which is not converted into liquid, it will pass through condenser. Okay, so the point is whatever exit of turbine is there, either it is what we can say total steam, or we can say it is some condensation has already done which is expected. So that stream enters into the condenser, convert the whole stream in liquid or in water, and then it passes through the pump. We cannot direct put the condensate sorry, we cannot direct put the exhaust of the turbine through pump. Okay, it will, because it is the mixture of pump, it is the mixture of vapor as well as liquid. So that exhaust of the steam turbine should pass through condenser, and then it pass through pump, and then preheater, reboiler and all that. So you can consider, you can recall the Rankine cycle and the usage of condenser. So these are some of the common chemical and petrochemical processes, petrochemical in terms of distillation and all. Okay, and in that way you can use the condenser in chemical and petrochemical industries. Okay, so these are some of the usage. Now as far as design is concerned, as far as design is concerned, we will focus on shell and tube type of condenser design, not air cooled type. Okay, so shell and tube heat exchanger you have already designed. Whatever would be the variation with respect to condensation, that we will discuss over here only. Okay, so shell and tube type of condenser, when we are considering, uh, if I see the geometrical variation. Okay, geometrical variation will be only this, that in that case the baffle spacing should be equal to shell dia. Okay, if, and this is also the case when condensation is occurring in shell side. If condensation is occurring in tube side, no need to worry about baffle spacing, it will remain as we have discussed for shell and tube heat exchanger. Okay, but in this case, if condensation is occurring in shell side, you need to consider wider baffle spacing, and that should be L equal to ds. Okay, so when you are considering the shell side, LB should be equal to ds always, right? Instead of 0.2 to 1 into ds as we have discussed before, that is not the case over here. And the reason for this wider baffle spacing is because you are dealing with vapor, you are dealing with steam. Okay, and the that what we can say, steam takes its space on its own. Okay, so when I'm having this wider spacing, it will be easier for vapor to take the space or take the place in the shell side and then proceed for condensation. Okay, otherwise what will happen, if that will be very less, it is difficult for vapor to move. Okay, that is one thing. So whatever baffle spacing we are considering, that should be equal to shell dia in this case. Okay, and when I'm considering shell and tube type of condenser, usually 4 configuration we used to have, like 4 configuration, uh, like 2 are of this type, what we can say, um, where the condensation is occurring either in shell side or in tube side. Okay, and how the condenser is placed, either horizontal or vertical. Okay, so in that way we can have 4 different configuration. Horizontal with condensation in shell. Okay, Horizontal when condensation is in tube side. Vertical when condensation is in shell side, and vertical when condensation is in tube side. Okay, so in this way we can have the four condenser where, based on what is the uh, what we can say, what is the orientation, and second where the condensation is occurring. Okay. So we will discuss all these four configuration one by one. First of all, I will see the that horizontal shell side condenser. Okay, horizontal means the condenser is placed horizontally. Okay, and condensation is occurring in shell side. Okay. Now, if this is the case, uh, in most of the process industry, these type of condensers are used in order to minimize the cost of support and facilitate maintenance operation. Actually, when we consider this horizontal placement will always be advisable to adopt when I deal with large capacity. Large capacity means large heat duty. Okay, so if Q of the heat exchanger, Q of the condenser is high, we can go for horizontal placement of the condenser. Okay, so in that way, you need to, when you are going for the design of condenser, you need to choose the orientation as well. Okay, so because until unless you will not choose this, you cannot design that. We will see further in subsequent slides. Okay, therefore orientation is that much important over here. Okay, orientation horizontally when we place, when I deal with large capacity or large heat duty. Okay, because it is easier to provide the support for large heat exchanger in horizontal way instead of vertical way. Vertical way, if you remember, the we have discussed in the last course, that design one, that vertical column, when we have tall vessel and all, for which support is very complicated to or very, what we can say, we need to design that very carefully. However, horizontal support, if I am having that, like saddle support and all, that is not as much complicated. Okay, and it is easy to place the heat exchanger horizontally and take out the whole bundle for maintenance and all once it is placed horizontally instead of vertical. You can imagine the difficulty in removing the bundle in vertical position. Okay, if the heat duty is large. Okay, so horizontal when we need to choose, when we consider large duty heat exchanger, and when we need to consider shell side condensation. Okay, shell side condensation, as I have told you that whatever bad we used to do, that we used to do with the tubes. Okay, so if vapor is corrosive in nature, okay, please keep in mind, if vapor is corrosive in nature, then only it will be allocated to tube side, otherwise always it will be allocated to shell side. Okay, because the coolant will be water. So if we compare the corrosive or corrosive nature of vapor and leak water. Okay, or we can say, if corrosive tendency you are not aware of, you can compare fouling, right? So fouling will be more in case of water. Okay, so if you are dealing with the what we can say, corrosive vapor, then only allocation will be done in tube side, otherwise always it will be on shell side, because water is has more fouling tendency, so it should be allocated to tube side always, right? I hope you are getting my point. How to find out, sorry, how to choose horizontal condition or how to choose the shell side condensation. Okay, when shell side condensation we need to choose when vapor does not have fouling tendency, sorry, vapor does not have corrosive tendency. Okay, usually vapor has very less fouling tendency, very less. If some particulate is there, then it will deposit, otherwise not. Okay, so corrosiveness is important over here to consider. Okay, therefore the condensing vapor is most frequently placed in shell. Condensing vapor is most frequently placed in shell and cooling water, which is usually more prone to fouling flows in tubes, that we have discussed already. So in this way I am having the horizontal shell side condenser, and in that case usually E shell baffled are used. Okay, so in that case you can consider the E shell baffled condenser we can use. Okay, there are few more points to consider, that it may have floating head or fixed tube sheet. The baffles are usually cut vertically for side to side flow and notched at the bottom to facilitate drainage of the condensate. Okay, what is the point to consider over here? Like when we consider the baffle, okay, usually we consider segmentally cut baffles. Okay, so these segmentally cut baffles, in normal shell and tube heat exchanger, these cut are horizontal. Okay, either it is cut from bottom or from the top, right? As I have already shown you the baffles, right? But in this case, condensation, when condensation is occurring in shell side, okay, we are discussing this one only. When condensation is occurring in shell side and it is horizontally placed, the baffle cut are vertical. Whatever segmentally cut baffle we are using, but that cut should be vertical, okay, not horizontal, because in that case we don't want sinusoidal movement. Okay, because it is vapor, and because of the lighter what we can say, lighter uh, weight of the vapor, or we can say less dense vapor in comparison to liquid, vapor always moves up. Okay, so when I'm having vertical cut, it is easier for vapor to move, so that movement will be from side to side. Okay, and when condensation will occurring over the tube, the condensate will deposit at the bottom. Okay, and it will what we can say, it will uh, some of the tubes odious, or we can say some of the tubes will be merged in the condensate. Okay, because obviously condensation is occurring continuously, so the liquid condensate that is available at the bottom, so some of the tube will be merged in this condensate. But those tubes which are merged in the condensate, it will not participate in heat transfer, because surface is not available for vapor to condense further. I hope you are getting my point. In that case, uh, continuous removal of condensate is required. Okay, and for that we usually have that baffle like this. Okay, if you consider this type of cut is there in the baffle. Okay, in this type baffle is there where vertical cut I am considering, and here I am having V notch. V notch, you understand, that is the simple V cut is there at the bottom, which allows the condensate to remove continuously, and the tubes will be available for vapor to get condensed further. Okay, so in that way you can consider the baffle, and baffle spacing will be how much? That would be equal to shell dia, that we have already discussed. And that is about the baffle. And one extra nozzle at the top of the shell is used to vent non-condensable gases. Okay, I will show that in this schematic. Okay, if you see here, I'm having this vapor is in shell side horizontally placed. Okay, and if you see this these baffles, okay, these baffle all, every time you will see baffle not cut but like this only, it will remain like this. Okay, because you are seeing from the side and cut is vertical. Okay, so when you see from the side, it will be the complete you can see the baffle, you can see completely from the side. Okay, now if I'm considering vapor over here, what it says that another side of this vapor is having another unit, and that we call as vent. Okay, the purpose of this vent is when the operation is not being conducted, uh, uh, we usually have air in this shell side. Okay, so when we inject the steam, that air will have some volume, though it will keep on compressing, but obviously it will accommodate some of the volume in which we consider the heat transfer area would be lost, and those gases or air we consider as non-condensables. So these vents are used to remove non-condensables from this side. So as vapor enters from here, at the same time we open this vent valve. Okay, and whatever gases, non-condensable gases are there, it removes from here, and the moment vapor will start coming from this, because that is the nozzle only na, it does not know whether it is non-condensable gases or vapor. So when vapor will start coming from this vent, we close this vent. Okay, assuming that the complete space is filled with the vapor, not non-condensable gases like that. So that is the purpose of vent, to remove non-condensable gases, and it will use everywhere where you are dealing with vapor or steam. Okay, either it is in the boiler, or if that it is flowing in the tube side, if vapor is in tube side, vent will available over here. Okay, so from one side, if vapor or steam is entering, another side vent must be there. Okay, so that is one thing. Another important unit to consider over here is to remove this condensate, because as I have told you that it is important to remove the condensate continuously. Okay, so if this is to do, here I am having the valve, and when this valve will open, the condensate will exit. Okay, but we need to ensure that only condensate should leave, not the steam. Okay, because this is the nozzle, okay, which we need to open. Okay, because we need condensate to remove continuously, so all the time it will remain open. Okay, but this vent we can close as vapor will start exiting from here. But what we can do over here, we need to remove the condensate continuously but stop the vapor and steam to lose. Okay, for that we used to consider another unit, and that we call as steam trap. Okay, that you must have heard in heat transfer course or somewhere, that steam traps we use. So there are different types of steam traps. This is one type which works on difference in density. Okay, so if you consider here at the exit, this valve is connected. Okay, this valve is connected with this. Okay, so whatever condensate and steam, because nozzle is not able to distinguish between condensate and steam, so both will enter in this chamber of steam trap. So here I am having that it is completely sealed, and here I am having this balloon. Okay, and that balloon will be connected with this valve, this gate. Okay, now what will happen, that when condensate and steam both will enter, because of the density, condensate will set at the bottom and steam will remain at the top. Okay, so condensate which sets at the bottom, and as it keeps on filling this space, it will keep this balloon up. Okay, if liquid will available up to here, this balloon will be up to here also. Okay, so the point is, because balloon is so light in weight and whole assembly is so light in weight, so that when liquid will be accumulated at the bottom, it will float the balloon, and that keeps the balloon up. And because of that movement of the balloon up, this gate opens up. Okay, this gate opens up, and as this gate opens up, the condensate will exit from here. Okay, condensate will exit from here. But as the level of condensate goes down, then only, because steam is there na, so then only steam will exit. But as the level of condensate goes down, it closes this wall. Okay, it brings this balloon down, which brings this wall down, and which closes this opening. Okay, so in that way we consider the steam trap, which is the important parameter. So when I'm considering the condenser, we need additional two units or additional two accessories, that is vent as well as steam trap. Okay, so that's all. uh, Hello. हाँ प्रीति, हाँ हाँ ठीक ठीक ठीक. So when we consider this vent as well as steam trap, it is, these are additional accessory in the condenser, and we will continue discussion on the condenser in next class. But if you have any observation so far, you please discuss. And that's all from my side for today. Okay, and don't forget to solve problem 1 and problem 2. We will discuss on Sunday. Okay, so we will continue condenser design in the next class. So thank you everyone for your patience. I'm literally surprised that no one is there except one, Jamuna. I don't know what is happening, why you people are not interested. Okay, fine, it's all from my side. Thank you.
Thank you, ma'am. Hey, wait, thank. बत्ती गएको त्यही भएर सबजना गाह्रो